Hello and welcome to a video lecture on the fluid mechanics of which is a course in Vtu BA Mechanical Engineering. So myself Dr.Raviraj from Government Engineering College, Chamarajanagar. So we'll move on to the next session where we are looking at module number 2, buoyancy and fluid kinematics according to your Vtu syllabus. So in the previous sessions we have learnt about buoyancy and also some concepts of fluid kinematics. So in this session we'll continue with some more concepts of the fluid flow, kinematics of the fluid. So wherein we'll look at one important equation called as continuity equation whenever the fluid is flowing. So continuity equation, as the name indicates, it is the equation which is used to calculate the rate of flow of the fluid in a pipe or in any through any cross section or through open channels, whatever it is. So as we have seen in the previous session, rate of discharge or rate of flow or discharge Q is equal to A into V. So that equation is used now. Suppose say we want to calculate, we take this is a pipe or any opening where the fluid is flowing. So this is the direction of flow of the fluid, and we take two cross sections. That at each cross sections we apply the what is called as the rate of flow or discharge of the flow at these cross sections. So the discharge at cross section 1 will be A1 V1, and if we take it as a compressible liquid or compressible flow, so we will be taking the density of the liquid there. At the cross section 2, density changes to delta 2 and also area changes, velocity changes. So we take rho 2 A2 V2. So at these two cross sections we take the discharges at the cross sections. So according to law of conservation of mass, you know that at whatever the amount of fluid is flowing at cross section 1 should be equal to amount of fluid flowing at the cross section 2. So with this conservation of mass, using the law of conservation of mass, we equate the discharges at these two cross sections and we get this equation. So whenever the fluid is incompressible, fluid flow is incompressible, delta 1 will be equal to delta 2, rho will be equal to rho 2, density will be equal, so we get A1 V1 is equal to A2 V2. So this is called as continuity equation, and we'll see how to use this equation in solving the problems. So we have one simple problem here. So we have a pipe with cross section 1 and cross section 2, and it is flowing, the fluid is flowing from left to right, and it's a diameter of the pipe is given at cross section 1 and 2. So it's a circular pipe, okay, where it is tapering. So diameter, it's not a straight pipe, its diameter is increasing, so it's a tapering pipe, and the dimensions are given in the problem. Velocity at this cross section V1 is given, okay, diameters are given. So using this equation, so we can find out. So velocity is given, diameters is given, that is area is given, you can calculate. So here area A2 is given, so area 1 is given, A2 we can calculate, velocity 1 is given, we have to calculate the V2. So it's a direct formula, this continuity equation you apply. So Q1 is equal to Q2, that is A1 V1 is equal to A2 V2. So this is A1 area, cross-sectional area at cross section 1, velocity at cross section 1 V1. So V1 is there, area 1 is nothing but diameter is given, it's a circular, so you calculate the area 1, V1 is given, diameter 2 is given, you calculate A2. So using this formula we can substitute this formula here and we can calculate the V2. Similarly, we have one more problem here. So here in this problem we have a pipe in which the fluid is flowing, and the cross section 1 we have the diameter or area and velocity, and here at the end of this pipe it is split into two pipes with different diameter and velocities, we can see. So at this cross section we have velocity 1, area 1 or D1, At this cross section we have velocity 2 and d2, area 2. At this cross section you take velocity 3 and d3 or area 3. So here we can, by observation we can say that a1 v1, that is whatever the flow is flowing here, the amount of flow is split into two parts. So the sum of these two, that is a2 v2 plus a3 v3, will be equal to a1 v1. So that understanding you have to make, and then using that you can see here. So a1 v1 is equal to a2 v2 plus a3 v3. So using this formula you can just substitute the values and you will get the velocity. You can get the discharge. So discharge is a1 v1. So discharge you can calculate, and that discharge will be split into two times, that is two ways. And if you apply this continuity equation, you can calculate the velocity at the third pipe. And similarly we have one more problem here. So here the pipe is given, circular pipe, diameter is given, and the fluid is oil, specific gravity is given. So you can calculate the density of the fluid, of the oil, velocity is given. So another cross section is given, so we have to find the velocity at this cross section and also mass rate of flow. So as usual you take area 1, d1 is there, area 1 v1 is there, d2 is given, you calculate a2, and v2 you have to find out. So you put the continuity equation and you find out the v2. So here he is asking you to find out the mass rate of flow. So mass rate of flow is nothing but the discharge. Okay, so discharge, that will be equal to rho into a into v1. So rho is nothing but density of the oil, specific gravity is given. So specific gravity into density of water will give the density of oil. So multiply the specific gravity of oil by 1000, you will get the density of the oil. So density of the oil is 900. So here it is asking you the mass flow rate, so density into this area and velocity will give the mass flow rate kg per seconds, because density will be in kg per meter cube. So into area is in meter square, then velocity is in meter per second, so this will give you in kg per seconds. So here we have one more continuity equation where I will be taking in 3 dimensions. So in the previous case it was continuity equation whenever the fluid was flowing, and with the masses, law of conservation of mass, we saw how the amount of fluid will be equal to amount of fluid flow in the other sections, cross sections. So here we have one more continuity equation in 3 dimensions. So it's simply a mathematical derivation. So here I assume the fluid is flowing, and in that we assume a fluid element of which is 3 dimensions. So it's having dx in x direction, dy in y direction, dz in the size of the dimensions of the fluid element is dx, dy, dz, and this is the center of the origin here, origin of these dimensions. So here we take again the continuity equation. So we take the mass of fluid. So we take this cross section ABCD. So the mass of the fluid entering the phase ABCD per second. So here the mass of the fluid will be rho into area into velocity. So the density of the fluid, velocity, you know, it is u. So we take the velocity in x direction as u here, and area of this cross section, it is y and z, is dy and dz. So this is the cross sectional area through which the element is flowing. So at this section it is dy and dz, so that will give the area. So the mass of fluid leaving the phase, so at this cross section the amount of fluid is flowing from left through this section, and EFGH is the right cross section, second cross section, and here the fluid is leaving. So using your differential equation, mathematical equation, so the amount of fluid flowing or leaving the phase, this phase EFGH, will be this much amount plus the differential of this amount. So with respect to x, del by del x, this much amount with respect to dx will give the mass of the fluid entering this cross section ABCD and leaving this cross section EFGH. So during this flow, gain of mass in this direction, x direction, will be mass through ABCD minus the mass through EFGH per second. So mass through ABCD is this one, rho u dy dz, minus the mass through this is the mass content here. So that will be this one. So we'll give minus minus here. So use your mathematics and you will get to this equation. So this is the gain of mass in x direction. That is with respect to del x, we have the rho velocity in u direction, dx, dy and dz. Similarly, you do the same thing in y direction. So in y direction, this is y direction, the flow, mass of flow is entering through CGHD and leaving A, B, F, E, this cross section. So we'll get this equation. Similarly, if you do that in the same z direction, in this direction, so mass of the fluid entering this bottom cross section, that is BFGC, and leaving this AEHD, this top cross section, will end up with this equation. So this equation you can simplify and we'll get this differential equation. So if you do your simple mathematics, differential mathematics will end up with this. And here we know it is del rho by del t, del u by del x, del u v by del y, del w by del z. So v is the velocity in y direction, w is the velocity in z direction. This we have seen in the previous sessions. So velocity of the fluid in x direction is taken as u, and in y direction is taken as v, z direction is taken as w. So you can apply this equation for all these kinds of flow. So if you take for steady flow, we know that the properties will not change with separate time. So del rho by del t will be 0. So we get this equation. So this equation, okay, this part will become 0. Now we are left with this equation. And even in this equation, rho density for incompressible fluid density is constant. So take out this density, we'll end up with this. So velocity in x direction, differential of velocity with respect to x direction, del u by del x, del v by del y, del w by del z is equal to 0. So this is the final equation, and this is called as continuity equation in 3 dimensions. And if you want in 2 dimension, you just remove any one direction, you will get a 2-dimensional equation, continuity equation. So we have one problem here. So the problem is we have a velocity vector. So velocity is expressed in terms of the vector here. So I, j, k are the vectors. So x, y, z are the velocities. X and y are the velocity. It's a 2-dimensional, and t is time here. So we have to find out the velocity and acceleration of the fluid particle at these coordinates. And time is 1 second. Okay. So as usual, we take the velocities. We will calculate the velocities u, v, w. So here velocity vector is given. So this part ui. So this is u. So u is this part. Then v is this j, minus 10x square y. That's the velocity in y direction. And w is nothing but 2t here. So k term is w, 2t. So using this coordinates now, we will calculate the du by dx and all those things. So here velocity components is already there directly, u is given. So we want to calculate the velocity at these coordinates x, y, z. So x is 2 here, y is 1, z is 3. So in this u, substitute the values of x, we will get 32 units. If you take v, substitute the values of x and y, 2 and 1, you will get 40. W is 2t, t is 1 here, so you get this. So velocity vector at 2, 1, 3 will be, so substitute this, v is nothing but this is u, so u is 32i, and y, j is nothing but this term, y term, that is velocity v, and k is the term of z velocity, so that z unit is, w is 2. So resultant vector will be the square root of u square and v square and sum of the square root of u square, v square, w square. So just add all these things, you will get the resultant velocity. And this we have seen in the previous sessions, how to calculate UVZ, UVW, and this is the resultant velocity. Similarly, acceleration we have seen in the previous session, how to calculate the acceleration. So acceleration in x direction is nothing but it is with respect to velocity in u direction, that is velocity u in x direction, all those things. So velocity acceleration x direction, you will get this equation. This equation we have seen. So this is a convective acceleration, this is a local acceleration. So velocity in ay is given by this equation, and velocity in z direction is given by this equation. So just substitute all the values. So you have to derive, you take the differential of du with respect to dx, du with respect to dy, and du with respect to dz. So you have to differentiate this term u with respect to x, y, z, and each term you have to take the differentiation. So if you do the differentiation here, you will get all the terms here. So du by dx is 12x square, du by dy with respect to y is 0, because u is 12x square. So differential of u with respect to y will be 0. So like that you go on taking all the terms, substitute that all these terms here, you will get ax, ay, and az. So the vector velocity acceleration vector will be axi, ayz, and azk. So x, y, z. So acceleration in all these directions. So substitute that, you will get 1536 I, then y is 320j, and z is 2k. So acceleration, resultant acceleration will be again sum of all these unit vector terms here, this and this, sum of this. So we'll get the resultant acceleration. Similarly, we have one more problem here. Velocity vector is given, u, v is given, and v, the second two cases are given. So this is the continuity equation in case of, so you take the continuity equation, make it 0, and you calculate, you take the u values, it's given here, del u by del x you calculate, del v by del y you calculate. So substituting these values in continuity equation, we get this equation. So we want del w by del z, so we just integrate that, you will get w in terms of x, y, z. So w is again a function of x and y. So w is this term you will get. So constant of integration is there. So it's a function of x and y. You can just keep it as it is. So you'll get the w. So in the problem, you have to calculate the third component of velocity, that is x and u and v is given. So w you have to calculate here, which satisfies this continuity equation. So take the continuity equation, substitute du by dv and all those things. So remaining you are left with del w by del z. Integrate that, we will get the value of w. So this is the velocity in third direction, w. Similarly, for second case, uv is given. So in second case, they are given v and w. So you have to calculate u. So take the continuity equation and you take del u by del x, and if you want u, you have to integrate that with respect to dx. So integrate that, we will get this term. So this is the constant of integration, and it's a function of x and so in this case it is x and y for w, and for u it will be, in case of u it will be y and z. Similarly, we have one more problem here. So you can solve this. Flow field is given, the vector is given, velocity vector is given, and you have to prove that it is a case of possible steady incompressible fluid flow, and you have to calculate the velocity and acceleration at this point. So you can do this, no problem. So it's so here we have to calculate this v. So this is the possible case of fluid flow. So velocity field v is given. So if you do this this continuity equation, it will be 0, then you can say that it's a possibility of fluid flow. So you have to prove that for possible steady incompressible fluid flow, this continuity equation will be equal to 0. So take all these terms, prove that it will get 0 here. And remaining velocity, as usual, you calculate for these coordinates 2, 1, 3. And you can calculate the acceleration also for 2, 1, 3. So do this, you will get the resultant acceleration in terms of the ijk, that is vector, acceleration vector, ax, ay and az. You calculate and substitute the sum of that, you will get these units. So this we'll stop here this session. So this session you have seen basically the continuity equation in 2 dimension and 3 dimension. So how to use this equation, 2 dimension equation, continuity equation, and 3 dimension continuity equation. So how to derive this and remember this equation. So this is the continuity equation in 3 dimension. So vectors, velocity vectors will be given. So you have to calculate the velocity and acceleration. And if this equation is continuity equation is 0, then you can say that it is a steady and incompressible flow. So in problems we have seen that, in the last problem we have seen that it is if this is equal to 0, then it is a possible case of fluid flow. So like this you can practice as many problems as possible, and you can learn how to calculate velocity and acceleration components in XYZ directions. Okay. Thank you for this session.